Hello dear learners, I am Dr. Vandana Yadav, Department of Chemistry, the Bhopal School of Social Sciences. Today we are going to discuss geometrical isomerism. In my earlier lectures, we have discussed about optical isomerism and which is one of the example of stereoisomerism and conformational isomerism. In this lecture, we are going to discuss the types of geometrical isomerism, their nomenclature, Cis Trans properties, methods of determination of configuration, EZ system and Sin and NT nomenclature. In the year 1875, Wonthoff and Labelle, they recognize another type of stereoisomerism in organic molecules which were having different substituted atoms by means of carbon double bond carbon. You can have a look at the structure, that carbon double bond carbon with two different groups on it. Like this, they were showing a different kind of geometry and that was called geometrical isomerism. Now, the very important factor about geometrical isomerism is that it will arise when carbon is bonded to a double bonded carbon. So, due to the presence of one sigma and one pi bond, there is restricted rotation. Like, have a look that if something is bonded with a single bond, that is freely rotating, but if you bond something with a double bond, then there is a restricted rotation. So, due to this restricted rotation, we have a new type of isomerism, that is geometrical isomerism. Now, though they are having same molecular formula and structural formula, but as you can see in the structure that the placement of these two similar groups is on the same side and here it is on the other side. So, due to the different arrangement of same group on carbon double bond carbon, we have another type of isomer, that is geometrical isomer. So, the important feature is that it is shown by only alkanes or derivative of alkanes and especially with two different groups attached to each carbon double bond carbon. As we can see in the structure, we have cis 2-butene and we have trans 2-butene. So, that means the placement of two similar groups if is on the same side, then we have first type of geometrical isomerism. If the placement of group is in the opposite side, then we have another type of geometrical isomerism. So, as you can see in the structure, due to the presence of one sigma and one pi bond, we have geometrical isomerism. However, in case of alkanes, you can see there is free rotation and in these structures we have conformational isomerism. To represent various geometrical isomers, we have three nomenclature systems. First one, which is very common, is Cis Trans Nomenclature. Second one is EZ nomenclature and third one is NT and Sin nomenclature. So, starting out with Cis Trans Nomenclature, Cis is a Latin word which means this side and trans is a Latin word meaning opposite side. So, as you can see in the structure, if the similar groups are on the same side, we call them cis. If they are on the other side, we call them trans. Moving on to their properties. So, though in the structure you can see the number of carbon, hydrogen and double bonds are same, but still what we observe is that cis and trans isomer, they have different physical properties, but due to the same number of carbon, hydrogen and double bond, they have same chemical properties. So, now the question which comes to our mind is physical properties. Physical properties means boiling point, melting point, solubility and dipole moment, which we are going to discuss in the later section. When we talk about stability of both the isomers, we will see that trans structure is more stable due to steric hindrance, as it is clear from the picture that two bulky groups are on the same side, which will lead to greater amount of repulsion. However, in trans, they are opposite to each other, which minimizes repulsion. So, hence we can say that trans structure is more stable, or in other words we can say that cis is more reactive due to its less stable nature. Methods of determination of configuration of geometrical isomers. If I give you two unknown compounds and I ask you to categorize them as cis and trans, so you have to undergo some test, or you need to know some methods through which you can categorize an unknown compound into cis and trans. So, first of such type is melting point. Melting point of trans isomer, as you can see in the structure, is higher than corresponding cis isomer. For example, you can see that malic acid and fumaric acid, they are having same number of COH, but melting point of malic acid is 130 degrees C and that of fumaric acid is 286 degrees C. So, trans structure is having higher melting point then corresponding cis isomer. So, based on melting point, we can differentiate between cis and trans. Next is dipole moment. As you know that cis, the two groups are on the same side, and in trans the two groups are on the opposite side. So, when you are having a trans structure, then bond moment cancel out each other and the overall dipole moment of the structure becomes 0. However, in case of cis isomer, you will have some value of dipole moment as the same groups are placed on the same side. So, based on dipole moment, we can also distinguish between the cis isomer and trans isomer. Now, moving on to solubility. Solubility of cis isomer is higher than that of corresponding trans isomer. What is the reason? As you can see from the structure, the cis isomer are less tightly held in the crystal lattice. Basically, what we call them U-shaped structure. U-shaped structure means two groups are on the same side. So, due to this reason, the molecules of cis isomers are less tightly held in the crystal lattice, and you can see from the structure that cis isomer is having higher solubility as compared to trans structure. So, based on solubility also we can distinguish between cis and trans isomer, but there are certain limitation of cis trans nomenclature, that is, this is not applicable to the molecules which contain 4 different connective substituent. Why? As you can see, if I am having C double bond C, I am having fluorine, chlorine, hydrogen and OH. So, from the structure you can see I do not have similar groups on either side. So, now we need to have one common group on both the carbon if we want to assign cis and trans. So, in this case, this is one of the limitation of cis trans nomenclature, that if all the 4 groups are different, then we cannot assign cis and trans. Second important factor is that cis and trans nomenclature do not discuss anything about those molecules which are not having carbon double bond carbon. How are we going to assign them cis or trans, or how we are going to distinguish between their geometrical isomers. So, now moving on to the second nomenclature is EZ nomenclature. This is used to specify the configuration of any carbon double bond carbon molecule by using set of certain priority rules. So, if you remember, you must have studied certain priority rules in RS nomenclature, and in this also we are going to study certain priority rules through which we are going to assign geometrical isomeric configuration on the molecule which is having all the 4 different substituent on carbon double bond carbon. So, we have EZ and EZ system, and priority rules are assigned by three scientists, Kahan, Ingold and Prelog. What does Z mean? Z means, it's a German word which means Zusammen, and it means the higher priority group should be on the same side. E means opposite. That means higher priority groups are on the opposite side. As you can see in the structure, I have shown that Z isomer with higher priority group on the same side. It is similar to cis, and higher priority group on the opposite side, which is similar to trans structure as we have earlier seen. Now, what are the priority rules? The very first question is, we need to understand what are the priority rules. So, rule 1 says that, as you can see in the structure, each carbon double bond carbon is having two substituent attached to it. On the left hand side carbon we have bromine and fluorine, and on my right hand side carbon is chlorine and hydrogen. So, as you know, fluorine is having atomic number 9. Okay, and bromine is having higher atomic number than fluorine. So, first rule says that the substituent directly attached to the double bonded carbon are given priority on the basis of atomic number. So, if you compare the atomic number of fluorine and bromine, bromine is having higher priority due to higher atomic number, and fluorine is having lower priority because of small value of atomic number. Similarly, comparing it on other carbon, chlorine is having higher atomic number than hydrogen. So, priority is assigned based on atomic number. So, we have Br on this side as higher priority group and Cl on this side higher priority group. Now, if rule 1 does not work, then what we are going to see that rule number 2 will be applicable. So, for example, if we are having hydrogen and deuterium, then they will be having same atomic number. So, if you are having isotopes of same element present, then the higher priority is given to isotope with higher atomic mass. So, in case of H and D, you all know that deuterium is having priority over hydrogen. So, in this case, the priority is with deuterium and H gets the lower priority. Similarly, here chlorine will get higher priority and deuterium hydrogen will get lower priority. So, we have second rule when we have two isotopes attached to carbon double bond carbon. Now, if above two rules are not giving you the priority groups, then we have the third rule. So, if the relative priority of two groups cannot be decided by rule 1, then it shall be determined by applying rule number 3, which says that if you have carbon and carbon which are having same atomic number on as a substituent, then you have to go on the next atom. Here it is hydrogen and here it is 2 hydrogen and 1 carbon. So, as it is clear from the picture that we have carbon with 3 hydrogen and here we have carbon with 1 carbon, hydrogen and hydrogen. So, comparing the mass, you can see that 1, 1 and 1 is lighter in comparison to this one. So, this gets the priority and this gets the lower priority. So, by using these 3 rules, you can assign higher and lower priority on the two substituent attached to carbon double bond carbon. Now, moving on to assigning EZ, just have a look at the example. On carbon, you have chlorine and fluorine. So, you all know that chlorine is having higher than 1 and this is 2. Then this side CH3 will get the higher priority and H will get the lower priority. Now, compare the position of higher priority group. In this, you are seeing that higher priority groups are on the opposite side. So, opposite means we are assigning E configuration. Okay, let's discuss one more example. If I am having OH and here I am having H, here I am having NH2 and here I am having CH3. Okay, so now starting with the priority order, in this side oxygen will take the higher priority position, and you will see that it gets the first position, this gets the second position. This side nitrogen gets the first position and carbon gets the second position. Now compare the position of higher priority groups. If they are on opposite side, then you assign E configuration. So I hope you are clear with the EZ nomenclature system. So we have another kind of nomenclature in geometrical isomer, that is syn and NT, and as you can see from the structure, it is applicable when we have carbon double bond nitrogen and nitrogen double bond nitrogen. So it is observed where we don't have alkenes. So especially when carbon is double bonded to nitrogen or nitrogen is double bonded to nitrogen, we use syn and NT for their nomenclature. You can see from the structure that if the OH and H are on the same side, this is the example of aldoxymes also, that if the OH hydroxyl group and hydrogen are on the same side, then we call it as syn, which is synonymous with cis, and if OH and H are on the opposite side, then we call it as NT, which is synonymous with trans. So this is used when we don't have carbon double bond carbon. This is all from my side. Today we discussed about another special kind of stereoisomerism, that is geometrical isomerism, which is specially observed in case of alkenes and their derivatives. We have discussed cis trans, EZ and syn NT isomers. I hope you all have clear understanding about the topic. Thank you.